atria contract, right, because these paths are still in place, right? The SA node's still firing off, so the atria get to contract, right? But the ventricles will not contract because it's like basically a roadblock. You placed a roadblock here, and then the path can no longer proceed. And so oftentimes that's why sometimes people need pacemaker surgeries to help with these blocks. Sometimes you hear an AV block. Sometimes SA nodes are not functioning properly, and so sometimes you need these pacemaker implementations to help with these electrical roadblocks. Yes?
So the pacemaker leads just go into the SA node, or do they also go into AV node?
You can do, there's a whole bunch of fancy things you can do with a pacemaker. So in the example I gave here with AV node would be blocked, they would have another pacemaker cell here that that would be hooked up to your SA node. And so it would feel depolarizations at the SA node, and then it would time it so it would send its own impulse down the bundle of His. And so yeah, there's a rich history of pacemakers you can look up. Wikipedia does a pretty good job summarizing the history. It's pretty interesting actually. Alright, cool. So we won't go into this too much in lecture. This is more something we'll talk about in lab. But using an electrocardiogram, an ECG or EKG if you're German, you can detect basically the path of this electrical conduction, right? And so this is what a typical ECG trace looks like for one cardiac cycle. And you have various waves. This bump here is called a P wave. This is called the Q wave. This is the R wave, S wave. Together, this whole thing is called the QRS complex. And then this is the T wave. Generally, what it stands for is the P is for atrial depolarization. The QRS stands for ventricular depolarization. And the T represents ventricular repolarization. And in lab we'll talk more about those in detail and talk about why you expect the voltage differences. So, sorry, this is time, and this is voltage. Usually measured in millivolts. And so you measure this thing with something called the Einthoven's triangle, where you can keep 3 electrodes in this kind of pattern, one on each wrist and one on one of your ankles, and then you can basically detect voltage differences between these 3 nodes, and then you can basically measure the ECG. This setup is called a 3-lead ECG. Nowadays, people do fancier things. So if you work for a cardiologist or you become a cardiologist, you'll do something like a 12-lead. Those are extremely fancy, and they show you conduction of the heart in all different ways of looking at it. So we won't talk about that too much, but yeah. Well, one thing you can do. So if you look at this is a really bad drawing of ECG. You can look at the interval between QRS complex, and you can calculate heart rate. And you'll do that in lab later, eventually. All right, moving on. Let's talk about cardiac cycle, right? The heart does contractions in a repeatable pattern, right? Everyone's heard of the lub-dub cycle, right? Well, that's essentially the cardiac cycle. The cardiac cycle represents what the heart does given one cycle of the infinite beatings it does, or near infinite beatings it does. And so, since this cycle, we're going to represent it as a circle, as a loop, and we're going to see what the heart does as it goes through the whole cycle here. So here, we're going to start here at step 1. And this is late ventricular diastole. So this is basically, diastole means the ventricles are not contracting, they're at rest. But this is also when the atria are at rest. So this is also atrial diastole. And so at this point here, the ventricles and the atria are passively filling. So meaning blood is flowing in from the veins, the inferior and superior vena cava, also flowing in from the pulmonary vein, and blood is just flowing in passively, just filling in like someone pouring stuff into the bucket. And that's created by pressure differences caused from earlier stages. Just keep in mind that things are relaxed, the whole heart's relaxed, and it's being passively filled. And then the second part is atrial systole. What does atrial systole mean? What's the atria doing? Contracting. And so that's what this red shaded part means. The red shaded part means pressure is being added to that chamber. By the contracting by the atria, you're adding pressure to that chamber, and that's what that red area means. And what happens is then the atria contribute their blood volume to the ventricles. And notice here it's a small amount of blood. It's not a lot of blood. It's about 20% of what's total going to be in the ventricles. And so people ask why you have atria in the first place, and that's a good question. And to tell you the truth, there's not a super good reason why. That's why you can have something called atrial arrhythmia. That means when the atria contract when they're not supposed to, and not notice it, because they don't really add a huge amount to what's being put into the ventricles. So the atria contract, and you can see that this segment right here is a segment where we say this atrial systole. That's what that red portion here, this inner circle right here, represents everything that's happening to the atria, and then the outer circle here represents everything that's happening to the ventricles. So this portion was atrial systole, and then we have this, S1. S1 is the first sound the heart makes. This is the lub. So that lub is one higher in pitch, but it's created by the closing of the atrioventricular valves. As those valves close, you hear that lub, the first sound of the tube beat of lub-dub. And that really kicks off the start of ventricular systole. So this is when the ventricles start contracting. And this is the first half of, the first part of ventricular systole is called isovoluminic ventricular contraction. So this means the ventricles are contracting. They're physically contracting, but the volume of the ventricles is not changing. Now, that's what the isovoluminic means. It means volume is staying the same. Iso same, voluminic, volume. But what is changing? What do you think is changing? If volume is not changing, what's changing inside this ventricle? The pressure, right? That's why we have this red shaded area. Sorry. That's why we have this red shaded area here. Show there's pressure being added. So pressure is being added, but for some reason volume is not changing. Why is that? Why are we not seeing volume changing? Yeah, because the atrioventricular valves are closed. That's good because we don't want backflow. We don't want to be pushing blood back into the atria. But also the aortic and the pulmonary valves are also closed. And so in that sense, I'll write it out. So the semi-lunar valves are still closed. Why? Not enough pressure. So in a sense, the aortic and the semi-lunar valves, the aortic and pulmonary, they are acting like mechanical gateways. They're not going to let blood go by until you reach a certain pressure, and once you hit that certain pressure, then it gets to relieve these valves. And so that's what's happening here. Before the isovolumic ventricular contraction occurs because we haven't reached that pressure threshold. But once we do, then we get ventricular contraction. Basically, those semilunar valves open up, blood gets shot into the aorta and the pulmonary trunk. And this is kind of the second part of ventricular systole. At the end of that, we have our second sound here. We have S2. This is our dub sound. And this dub sound is created by what? The closing of the aortic and pulmonary valve, the closing of the semilunar valves. And so whenever you hear the lub dub, these are just the closing of valves, closing the atrioventricular valves, and then closing of the semilunar valves, the aortic and pulmonary valves. And then we have this part, this last part of isovolumic ventricular relaxation. So you notice here we're now in a region where both the atria and the ventricles are in diastole. That means they're both relaxed, they're not contracting, and blood is flowing in. But why is it ventricular? So it's isovolumic ventricular relaxation. So that means the volumes of the ventricle are not changing, right? They're staying the same. I just told you the blood is flowing in. Why is the volume of the ventricle staying the same?